though the topic is about the evaluation of LLMs, how many of you have programmatically developed an app with an LLM? Just a quick show of hands. Okay, I see roughly 10 to 12 hands. Okay, fine. And how many of you have done some evaluation related metric follow up? Okay, see, just hardly a couple of them. Okay, awesome. So okay, so this thing is going to be a little interesting and new to the others, and for complete newbies, I think the first slide will be something. Old habits die hard. So this is the only mathematical slide. I'll just confess that. So because this is basically the heart of the LLM, the transformer. So we need to understand a few things about the transformer so that when we try to evaluate certain things in terms of cost, compute, speed, power, user experience, all that we kind of operating on are some of the parameters which come out of this. So we'll understand a little bit of the fundas, a little deep dive into that, and then we'll get into all the practical inventors. So let's start from the bottom. So you guys all know that this is a 2017 paper of Vaswani, and that's the typical transfer block. This figure though is a nice figure given by Sergey Levine from Berkeley. So this is a very nice snapshot of what's going on, what part of the transformer is really doing what. So if you can see at the bottom, the input is basically kind of positionally encoded, and you give the tokens. So the first major activity that's happening is inside that multi-headed attention. Okay. So just to revisit quickly, so multi-headed attention takes your queries, and it also there's a query matrix, there is a key matrix, and there is a value matrix. Typically, they make the query and key matrix dimensions aligned. The value matrix could be of any dimension. So the intuition is basically if you do a QK transpose, so the number of rows divide into number of dimensions because you have a transpose there times the number of rows, you got number of rows by number of rows. So basically what happens is your tokens are assembled together, stacked against each other in a square matrix. And what you basically develop is a context. If I say I went to the nearest cinema theater to watch X movie, what did I do, where did I go, what was the nearest theater where I am, all that context is kind of self-built in this attention matrix that we develop. That is QKT. And just because of some numerical stuff, we divided by square root of the dimensions in which we projected this embedding. So that's like QK transpose divided by root T. And then you take a softmax, you kind of make this normalized value between 0 to 1. And the weighted value vector is how you represent a context. Okay, that is how you build a context inside that one block. Okay, we have to be very clear with that. Now I want you to think about two things here. When you build this context, there was this dimension D involved. You could have raised it to 512, 1024, whatever it is. That dimension is of key importance to us. The second thing that is of key importance to us is the context length itself, and the QKT, that is very important because that's a floating point operation for us, right? Because a floating point operation is the most important thing for us because we have a budget for our hardware, right? So those are the main factors in that block. So if you go one block higher, you take this attention matrix and you take the prior representation and you do some layer normalizations, and as you feed it forward to your affine transformation W transpose A plus B, so you learn that W, W1 and W2, and there are some bias terms. So again, you got a structure for your W's. Those are your learnable parameters. They have a size. Okay. So there are, now we started with QKT and the flops there, the root D, the dimension involved. There are some learnable parameter W's, and this whole block keeps stacking one over the other. This is the encoder side, and there are some details in the decoder side, but I'll just skip that unless we need those details later. So you stack block after blocks like this, and if you look at this here, this means that you stack n number of blocks. Typically, depending on the size of our architecture of the LLM, we'll have anywhere from few tens of blocks to even a few, in the higher tens of blocks to even sometimes hundreds of blocks. So all the context, you learn the lower level context, and you learn the little bit of higher level context based on the lower level context, and this hierarchy keeps building. This is what is happening. All this is happening through a bunch of floating point operations in terms of matrix operations. Now, one thing I did not mention here is, in that self attention block, it's not just one head. As I said, there could be different things that we might develop context on. So there will be multiple heads. One head will just track probably the adjectives. One head could track the nouns if it's an English sentence. One head could track the dates or whatever it is. So you can give as much provision as you want. It's just that the number of floating point operations will keep increasing and your architecture will keep becoming complex. Now we'll go to the next slide. So as long as we have a common basic understanding of this, what is really happening in the evaluation metric dimensions? What are these dimensions and what are these metrics before we get into all of them? So my co-speaker Ronit is going to show some examples, and he's also going to get into some of these metrics in detail. But again, let's take a fair bit of time to understand what are the different things that we evaluate our LLM on. We just don't evaluate our LLM on the pre-training efficiency. So all that we spoke about in the training phase comes under pre-training efficiency. As I said, we have a specific budget. So many flops we've got our access to hardware, and based on these flops, we need to make sure we train the right amount of data and we pick the right amount of complexity in architecture, so that when we really the evaluation is like a life cycle, right? So how is our LLM evaluated during the training process, during the inference process, and during the fine tuning process? How easy it is, or how difficult, how complex it is. So while training, we need to understand the number of parameters, the number of data points, and the representativeness of the data points that we train on, because that's going to directly reflect on the evaluation parameters of the LLM. One parameters could be accuracy, where it could directly do it. And we'll talk a little bit about RAG and other kind of nuances we can introduce later. And the flops, because flops is kind of fixed. It's a given budget. It's a deterministic function. So I'll give a gist of some of the insights from the latest paper from DeepMind, where they kind of they walk through their journey of how they created Chinchilla. Chinchilla is again an LLM, which is kind of an offshoot of Gopher, an optimized version of Gopher based on all this computed efficiencies. Now, the second thing that we need to think, as I already mentioned, is we don't want to just optimize it for pre-training, but we want also to optimize it for inference and fine-tuning. And why do you want to do that? Because our inference and fine-tuning is also in the whole energy cycle. We want green LLM, so we want low energy during also the inference and fine-tuning. So it's kind of a life cycle. So let's have that in mind when we think about this. The second important dimension that we have to think about while evaluating an LLM is from a user perspective, what is the context, clarity, and precision that he is expecting and getting as a response from the LLM. These are very important. So there is a very important metric called chain poll. How many of you have heard about chain poll? Quick raise of hands. Okay, so yeah, so this comes under the context of how do you reduce hallucination, and Ronit, you're going to talk a little bit about this, right? So there's a data set called Real Poll, out of which they benchmarked several data sets. But the idea behind that is you want a query to give a response which is correct. That doesn't mean that it should be conversationally not very unwieldy. It should be conversationally wieldy. It should be correct. At the same time, it should adhere to a context. Like it can be correct, but it can be something which is slightly off context. So how much it adheres to the context and the correctness of it, both of them kind of put together give you that kind of metric called chain poll. We'll touch a little bit about that. So we spoke about the whole life cycle evaluation. We spoke about the power, the cost, the cost in terms of flops indirectly, power in terms of the green LLMs, the life cycle evaluation in terms of every activity we are trying to optimize. Second dimension is the correctness and the context adherence which we want. The third thing is you want also the user generation speed, the tokens per second. You don't want it to be too slow so that you read and keep waiting for it. So we'll talk a little bit about concurrency and how do you set up all this. That is the third dimension. The fourth dimension is directly on accuracy, accuracy of the response. Uh, Here we've got a bunch of things. There's something called ARC, accuracy in reading comprehension. There is MMLU, massive multitask language understanding, I guess. So basically what they have in MMLU is they've got some 16,908 multiple choice questions, and they cover a wide range of topics. So whether you're able to generate your embeddings and do this whole LLM process, and whether these embeddings are representative of the correct response, how accurate they are, that is kind of handled by this. Chinchilla, the one that I said, which DeepMind created, that had a very good MMLU ranking. I think it bet the Gopher model by a 7% or something. Probably we'll have a slide on that. There's another accuracy benchmark, LSWAG. It just evaluates the common knowledge, and there are other metrics in general for language evaluation when it comes to language. Recall oriented understudy for gisting evaluations. So you basically take a query and you get a response. You benchmark that response with you get a bunch of such responses. You benchmark all of them with a reference benchmark. You actually benchmark all of that with a reference. So then you kind of get a dot product and you see how close you are. ROGL is the number of maximum subsequences that match, and there are some nuances there. And you might have heard about, it's not blue, it's BLEU. I'm sorry for the typo. So there's a language understanding evaluation glue, and there is a bilingual language understudy evaluation, that is blue. These are again very similar. One is used for translation tasks, blue to be precise. So there are a few of these cost, life cycle, power, context, user experience, accuracy, and the language level understanding and human level understanding, and the diversity, heterogeneity, and variety of datasets in which it can. So these are the basic things you'll have to think when you think about how do you evaluate an LLM. Okay, now we'll go a little bit about what DeepMind did with Chinchilla so that you get an idea of what happened in that study. So Gopher, as you see in the second bullet here, so this one is, I don't know if you can see, okay, you guys can't see in the second bullet, Gopher to 280 billion. So they took the Gopher model, it's a highly complex architecture, 280 billion parameters, and they tried to reduce the model size, and they kind of doubled or they quadrupled the amount of data that they used to train that reduced model. So typical the typical thumb rule that they followed while they undertook this study based on previous literature was, if you kind of increase your architecture complexity, you also need to give more amount of data to train. So that's kind of something that previous literature had established. They started with that and they kind of took this complex architecture, but they kind of reduced this complex architecture to like 1/4, like 70 billion. Chinchilla is 70 billion. But at the same time, the amount of data that they kind of quadrupled. I think they use some 1.4 to 1.5 trillion tokens. They actually found that this particular, it's given there, 1.4 trillion training tokens. Yeah, sure. Thanks.
It's a pen, like,
yeah, it's a pen. No, I think it's okay. It's okay. Perfect. So, so you got 1.4 trillion tokens, as you see there. That's the training tokens that you use, and they had a 70 billion model. This model actually might have it here or have it in the next slide. It actually improved the MMLU benchmark by 7%. I think the previous SOTA was 60%, and this went to 67.5. So one of the things that they found was it's better to have for a given flop, and it's not just like reducing the model complexity. You have a flop budget. For that flop budget, you have two levers. You can reduce the model complexity. You can increase the data. So this the hardware budget you have is deterministic. You know what you have, the flops, and for those flops you can calculate your loss function, the way your loss function comes down. You can see all the values, the way your loss function comes down. You can settle on a certain accuracy, and for that accuracy you can reduce the model complexity and increase the data, or you reduce the data and keep the model complexity. You can do all these studies, and they finally came out with Chinchilla. So basically what they meant is a reasonably complex architecture with lot of representative data being trained gives a good output on the evaluation metric. Here the evaluation metric they used was MMLU, massive multitasking language understanding. That 16,000 data set where you have a multi-level reading comprehension, multiple choice questions. So they have a few approaches, but that's not very important right now for us. Um, Now, going back to the first slide, and this is why I put that fundamental understanding. How do you reduce the model architecture? There are two, three ways in which you can do. I said there are multiple layers. You can reduce the number of layers automatically. The amount of super context that is being developed keeps reducing. Second thing is the number of attention heads you can reduce. If you reduce the number of attention heads, your QK transpose, the flops operations keep reducing. That's another way. The key value size, you don't need to really, and the dimensions of the model, that directly again is representative of your dot product operations. Okay? So there are several ways in which you can reduce or increase the complexity, and you can also increase the batch size. You can play with all those hyperparameters. Now here are the number of tasks and the example data sets from which they created these tasks for their benchmark that we saw on the last slide. So this is what they did for Chinchilla. This was the work done by DeepMind. The second important thing, the way they think about evaluation, uh, is something called uh, the bit the bit per byte metric. There's something called bit per byte. How many bits are you spending to carve out one byte of response? That is what it basically means, and it's given by a very simple equation, a simple function, which is L times log of E, which you see on the top right. Basically, L is your loss, which is primarily your cross entropy loss, right? So you got a true distribution with the labels, your data labels, and you got your predicted distribution, and you do a negative log likelihood. That's basically what cross entropy is. So you basically do that, and you get this bit per byte. Here, as you can think, the lesser the bits that you spend for getting a certain, carve out a certain byte, it is better for you. And here you can also think about how, if you think about how to optimize this, um, you can think about these three strategies. Uh, you can think about distillation, right? I mean, so you have a teacher model, and with a very, very reasonable loss of accuracy, you kind of develop a student model, and that has fairly large reduction in terms of number of parameters. So that's a good. That will also improve your BPE, which means it will reduce your BPE. That's the improvement dimension. The second thing is you can prune. If there are very insignificant weights, you can prune all those weights, and it does not significantly affect your BPV, uh, bit per byte. The third thing is you can do quantization. You can use bfloat. That's another way, but that's another topic in itself. So let's not get too much into that. So these are some strategies in which you can improve your BPV, bit per byte. That's another very good evaluation metric if you think about the whole life cycle of an LLM. So now we can talk a little bit about the LLM challenges. It's a good way to good time to segue for Ronit. You can take over, and we'll come back and do some questions.
Hi all, good morning. I'm Rohit, and I'm looking at slides about in review of progress. Yes. Oh, should I start from? Okay. Okay. So, yep, there will be model limitation and also cost associated with running inference and training. As most of the LLM apps are hosted on our own servers, and that is, we don't use the client's PC or mobile or anything for inference, it will cost us a lot. So the limitations of LLM usage include uh, the LLM might not follow the instruction that we give it. Like as a system prompter, we would ask it to do something, and after like maybe a few number of messages, it might go off, and that poses an issue because if we have an app which is supposed to be a therapist and it starts talking random things to the person, it will cause issues and it will be a negative remark for our app. And the next thing is hallucinations. So if you ask an LLM something, and if the data is not in its training set or it does not know about the information, a lot of the times it won't just say that it does not know. It will try to tell a few things which are not true, and this is an issue when the model size is very low. Like if it's a 7B model, if you ask it as normal GK general knowledge question, it might give a wrong answer. We can fix this by using a larger LLM, but that increases the cost. So the next thing is it can generate harmful content, and yeah, that's pretty self-explanatory. And the next part is limited contextual understanding. As Sir explained, we have a limitation for context, and as the context increases, we also lose prior information. This is the problem with our encoder decoder model, and that's something that attention fixes, but it can't fix it completely. So we need a way to actually keep the context. And the next part is lack of reproducibility. Uh, in our testing, the model might give some results, but when the user starts to converse with the model, it might give some different result, which might not the thing that we want. Okay. So yeah, the first thing that we can try is to evaluate our model. So if you're not using a model like ChatGPT or something that's not hosted, let's say we are fine tuning our own model. So first thing that we have to do is actually to evaluate the model. These are the standard evaluation techniques that are used. MMLU, which Sir has already explained, and also HelloSwag and Human Eval. So MMLU, you just give the model a few multiple choice questions and ask it for an answer. And it closely relates to how we learn and we answer things. So and there are few ways in which it's evaluated, like zero shots and few shots. In zero shot, you just ask it a question and it answers, and we evaluate on that. And in few shots, let's say we are taking like five or six queries, and we just give it like a process. Like we just ask it like, let's say if you want to know something about space, we'll first give it some context, give it some information, and then we ask a question. That's the two ways of evaluation that we have. And the next thing we have is Hella Swag. It is more on how the model knows about common knowledge. The MMLE was mostly based on how much knowledge it has and knowledge about different things. HellaSwag more correlates to like its general understanding and the way it can respond. And then there is human eval, which is more focused on coding evaluations. So if you are developing an AI assistant to code like Copilot, you might want to use human eval. And there are other methods also, maybe you can also hire a person to actually do it for you, but it will be very costly to actually do that, because you can't go through like hundreds and thousands of questions and ask a person to evaluate it for you. So the issues with the current evaluation methods are, you could see that even like the smaller parameter models uh, have like very good MMLU scores. That does not mean that it has a lot of knowledge. It just means that the MMLU, the training that the data set is actually included in the training data set of the model. So it will be able to answer things that's in the MMLU, but it does not have actual knowledge about everything. So yeah, that's one issue. Once your like evaluation metric is open source, it gets added to the newer models training data set. And for like as we are developing our own LLM based apps, we don't actually have a evaluation metric for app based things. MMLU is basically asking it for general information, right? We don't actually have something to evaluate our app, like our specific use case. We'll have to actually develop something of our own. And the next thing is perplexity, which like it tells us how good the model can predict a text, but it does not actually tell about the understanding of the model or things like that. Like, yep. And again, human evaluation is possible, but it's very costly. So let's say we have an app and we have fine-tuned the model also. Now, how can we do it? How can we evaluate our model? Let's say our app uses function calling. So we'll be giving the LLM some information, and function calling basically is just giving the data in JSON formatted text, and then we ask it for a response. So what we can actually do is to run instrument test cases and ask the model to give an output, and then we compare it to the ground truth. This is the easiest way that we can do it. We'll go on to other methods that we can try. Okay. The part which would like to actually go in deep is evaluating hallucinations. This can be an issue like when you are creating an app. Let's say it's a chatbot for an flight booking app. So if your model starts to hallucinate about flights that does not exist, it will be an issue. So yeah, we need some way to actually quantify the amount of hallucination your model is doing. So yeah, this is the basic flow of how we would do it. So we'll have a data set of text inputs. So for our app, let's say the flight app, we'll be like book me a flight from Bangalore to Calicut, and we have a data set of these texts and also the responses that the LLM needs to give. And now we'll get the completions from the model, and we'll check the hallucination, like what is the difference, like how not the difference, like if there is a difference, it's fine. If it's saying something out of context, then it's not fine. It's the issue. So we can categorize hallucination detection into two: open domain and closed domain. In open domain hallucinations, the false claims about the world maybe made by the LLM. In closed domain, let's say we have given it a context and it's straying out of the context. That's closed domain. Okay, now the challenges are before like the ChatGPT and other sort of models existed. There were other models which hallucinated a lot, so detection was very easy. So the things that we already have, the models that we already have to actually test hallucination, does not perform well now. And also there is a huge amount of cost that's related to this, because our LLM needs CPU, and also to compute the hallucination, we also need GPU compute, because and if we are using a fairly big data set, that will take a lot of time and it will cost us a lot. And again, it's impossible to prepare a ground truth response for every conversation an user might have. Yep. So this is one of the evaluation metric as self-check GPT. It's a process in which you can check how your model is hallucinating, and this does not need human intervention while doing the test. So it just asks the model uh, as the name implies, it's self-check GPT. The GPT will first generate an output, and we ask the GPT, "Have you hallucinated?" Now this can be done using a chain of thought process. First, we'll ask it a question, and then we'll give it a chain of thought, like to actually go through every step it has done. Now a lot of the times, due to the way that LLMs works, it's basically next word prediction, and also it has a lot of context. So if we take in the mathematical sense, in an n-dimensional space, if this is a word that's like hello, and the next word might be my, and so if I'm introducing myself in that context, it will be hello my. The next word should be name. So in mathematically what happening is that hello hello gets connected, the hello vector gets connected to the my vector, and now using an operation we are finding the next word, we are supposed to get the next vector, we are connecting the next vector, so hello my name. It can go like that. So more context that we have, like more context that we can keep in memory, we can also keep hallucination low. So something like chain of thought, which forces the LLM to go through every step, uh, can actually reduce the amount of hallucination it does. So, but the user won't be asking questions like that. The user won't be asking it to do chain of thought and all. So, what we can do is first we'll simulate what the user might ask the model, and then we format the question as chain of thought, and we can ask it we can ask the LLM if it hallucinated by giving it the input and output that the user gave. Okay, this is self GPT explanation, and now we can. There are ways to also check how different the output is, like blue score and also bird model. We can use that. So I think you know about Blue Score because it has existed for a while, and not just for LLMs. Blue Score was introduced for machine translations. So it just quantifies the difference between the actual output and the output that was generated by the model. So we can also use that in LLMs. Okay, the next thing is chain poll, which is something new and which is something that does not need as much computation power as the other methods. So chain poll, you can see the uh, scores and the UROC scores, and real hall is the data set that they created because they are arguing that the current data set that we have that we had is not that good. So we'll get into how chain poll works. Okay, this is the thing I already said. The pre-existing datasets to evaluate hallucinations were like deficient on data. So real hall actually contains four datasets carefully selected for challenge, realism, and task diversity. It can find the inconsistency between the generated text and the reference text. So there are two types: a real hall closed and real hall open. In real hall open, you just ask the model for an output, and then you compare with what ground truth that you already have. In open, uh, yeah, in open, you don't have that ground truth, and you'll be using the chain of thought methods itself. Okay. So evaluating hallucination using real Hal close, because mostly when we are creating an LLM based app, we would know what we should get. It's not like maybe you have a RAG, maybe you can search information from that. So we already know what we need to get. So this is how they did it in their paper. It contains, and in the paper, in the chain poll paper, the real Hall closed dataset was created using two datasets, the COVID QA and drop dataset. The COVID QA dataset is basically questions about COVID-19 and their answers. Uh, and drop is just an open book dataset that requires like reasoning and all. Okay. In real hall open, we just give it trivia questions and all. Trivia QA was used to test like humans like ability to answer questions, and it was more like a like open book test. But now we are not doing that because the LLM has a lot of context. It already should know these information, so we just give it the questions and we expect an answer. uh, Okay, this is the flow of chain pool. This is how they did it. So instead of GPT 3.5 Turbo, we will be using our own model. And we'll first generate the output for our input from our model, and then we can ask the model, ask a bigger model if you are using a smaller model like Mr. Assembly or something. So we'll ask a larger model how much it hallucinated or not, and the prompt will be of chain of thoughts format. You will ask the model to go through every step, like how to think to get to an output, and we'll run like these steps multiple times, because maybe every time LLM generates a different output. This is due to the system fingerprint changing, and also the random number changes, everything changes. So a lot of the times the output also might change. So now we just divide the number of yes from step 2 by the total number of answers to produce a score between 0 and 1. The yes is to hallucinate, if it hallucinated or not. So it's fairly simple test. Yeah, so these are the scores that we got. So it's said that a chain poll is state of the art right now, and it has an average AUROC of 0.772, uh, and it's better than the self-check model that I showed to you before. So there are two versions: chain poll correctness and chain poll adherence. In chain poll correction, it's about open domain hallucination, and in chain poll adherence, it's about closed domain hallucination. With these two information, you can actually understand if you're in with chain poll adherence, you can understand if your model is going out of context, saying something it should not say. And in chain poll correctness, you can know how correct your model is giving responses. So yeah, these are just the graphs of ERS, ROC curve and President recall. And you can see the team pool is scoring much better than others on their real hall data set that they have created using COVID QA and drop. Okay, now continuing to the next part, which is the cost issue. So if you are going to develop an app and if you are going to get users, you need a lot of GPU compute. And a good LLM app should also be able to at least generate 10 tokens per second. If it's generating one or two tokens per second, that means like maybe one word per second. The user might not like it. So this is the measure that I got from internet, that you should be able to at least generate 10 tokens per second. And we should be able to create a new LLM framework, that cost evaluation framework that, given the model and the max context size, gives the cost per number of users. So so it will make it easy for you to actually predict how much the spend will be, and also to optimize the cost of the app, like the subscription. If it's a subscription based app, you can actually uh, optimize the like subscription amount that you have get from the user. So yeah, you can have something like this where you upload your model to Hugging Face, and it will get the parameter size and estimate memory usage. So I have used the Llama 270 set for this demo thing. So at a 16-bit floating size, it takes around 13 GB of memory. And here again, the flops estimator is how many flops it will take to inference for that model. So here the layers are the hidden layers, the vocabulary size, the context size, and the hidden layer dimensions. Again, how many weight, like the dimension of the hidden state, and attention heads is 32 for this model. So I can get an estimated number of floating point operations. And finally, we can actually calculate the LLM cost. So let's see, there are 4 users and the model parameter is 7 billion. And the GPU memory used is auto-filled, and also the average context size. Let's say a user uses about 2048 tokens in both input and output. So the estimated inference cost would be around $0.9 per hour for 1 hour for this use case. Okay, now we can actually add a few stuff like we can compare with this information. We can compare how what bits and bytes we should use for our model. So again, as I sir has explained, quantization is a method where you can actually reduce the complexity of the model, and to also reduce VRAM usage, which uh, can help you to run multiple models. So and also to increase the context size. So yeah, so we can also compare that and finally get to a like conclusion, like what quantization we should use and how much it will cost for us to run that. Sir, should I explain Video Llama or do you want to do? Just talk a little bit about Video Llama and that. Okay. Okay, so the next part is something new that we have found. It's called Video Llama. It's a multimodal multimodal model, which means it's also able to use videos and also audio. So this is how it works. We have two models before the actual uh, input gets to the LLM. So the basically the flow is you just give uh, video you just give Video Llama the video. It the video is passed, like after splitting the audio and video track, it's passed to two other models, which the first one is the visual encoder and the second one is the audio encoder. So once after passing through that, these encoders will generate text for the LLM about the video and audio. Now, as the LLM has context about what the video and the audio is, it can actually answer the questions about the video. Yeah, I just wanted to touch on the multimodality of the models, so we can incorporate this in our apps. This can be useful in where you have interaction with users and you can actually extract the emotions from their audio and also uh, their facial like expressions and all. Yes, sir. I'm done.